All right, so we talked a little bit about isomers the other day, so let's talk about them formally. So what we've been working on is a structural isomer, molecules with the same formula but different bonding structure, right? So isomers are possible when you have larger molecules. So the first isomer we see in the alkane family is with butane. There's two isomers. So your straight chain, this would, that's actually not butane, here's butane, C, 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 C. This would be N-butane, right? N just refers to the straight line version. Or we have C4H10 that looks like this, which would be 2-methyl propane. Now, 2-methyl propane, oftentimes 2 is disregarded. Sometimes this is just called methyl propane. Why is that okay? Because you can't put the methyl anywhere else. If you put the methyl on carbon 1 or 3, it wouldn't be propane anymore. What would it be? Then it would be butane again, right? Okay. All right. C4H9Cl, this is what we call an alkyl halide. And basically it means there's a halogen. So if there's a halogen on something, where are all the places we could put it? Well, we could put it at the end, or you could put it on the second carbon. Anywhere else? How about the third carbon? Third carbon would just flip around and be the second carbon again. Okay? All right. We could do this. We could break off one of the methyls, put it also on carbon 2, so that you have a methyl and a chloro group on the second carbon. So this would be 2-chloro 2-methyl propane. Chloro is the prefix for chlorine, bromo is for bromine, fluoro is for fluorine, iodo is for iodine. Okay, it's not uncommon at all to see halogens bonded to alkanes and form alkyl halides. Okay, so geometric isomerism. So we talked about alkenes, but we didn't talk enough about alkenes. So alkenes have a specific property about them that's called cis-trans isomerism. So let me explain. So let's say we had an alkene like this. Okay, so you would look at this first and you would say, oh yeah, that is 2-pentene, right? Remember the ene for the double bond, the 2 because the double bond starts on carbon 2. Okay, so the reality is this. Remember how that each carbon atom is by default what kind of hybridization? sp3. But if there is a double bond on a carbon, that reduces the number of bonding domains down to 3. Okay? So what this really means is there's 2 variants of this. And it has to do with that sp2 hybridization. Remember how we don't draw in hydrogens just because they're everywhere? We just assume they're everywhere. But if we did draw in hydrogens, then it might become apparent that this is a possible structure for 2-pentene. Does that picture make sense? Okay. The double bonded carbon is sp2 hybridized, which means it has to take on that trigonal planar geometry, that 120 degree, roughly 120 degree geometry. All right, but who's to say that the double bond or the chain on the other side, these guys right here, who's to say that they're at this angle? What if they were at this angle instead? Well, that actually does happen. Every time there is a double bond, there is a plane that we cross over. And where that chain continues on, which plane it's on, this is the plane I'm talking about. Imagine if you just folded this like a piece of paper in half. All right, so where the double bond is, you're either on the top side or the bottom side. So when both carbon chains are on the same side of that fold. This is what we call cis. The cis prefix that we're going to use is for when they're on the same side. So this now becomes cis 2-pentene. Again, cis means it's on the same side of the fold. Okay, but in the second example, here, we've got our carbon chain above the fold, then we have the double bond, and we have the rest of the carbon chain below the fold. So they're on opposite sides. So this has a different name. This is what we call trans. It's crossing over. Trans to pentene. So these two are geometric isomers. So if I asked you to draw the isomers that exist for C5H10, right, you would have to take into account that the cis and the trans are two different isomers. Okay? All right. In these examples here, for this compound C2H2Cl2, the two carbons are double bonded in the middle. Here, your bonds are shown. We have two chlorines on the first carbon, two hydrogens on the second carbon. But we very well could have that mixed up. You could have one of each. Or you could have one chlorine per and then one hydrogen per. Now these two here are not the same. And the reason why they're not the same is because double bonds cannot rotate. Single bonds, yes. So they're literally locked in. So you would normally think, if this was a single bond, that this carbon would spin around. And as it spun around, the Cl could be here or here, right? But if it's a double bond, there's no spinning. They are fixed in place. And that is why they are two different structures. Okay? Okay. So in pharmaceuticals, one of the most important concepts that you will study is optical isomers. And optical isomers have to do with the fact that nearly all organic compounds are rooted in carbon, and all carbons can make 4 bonds. Now, if you have 4 unique groups bonded to a carbon, like in this situation here, okay, so on the left we got a hydroxyl, right? On the top we have a carboxylic acid group. Then we just have a hydrogen on the right, and then we have a methyl group on the left. There are 4 groups that are different from each other. When this happens, this is what we call an optical isomer, or it's called an enantiomer, is the technical name. And the reason why this even exists is because if you built a molecule using balls and sticks, like we did in lab, different colors, what you'd realize is that this shape here and this shape here are not the same. They look the same on paper because on paper we drew it as flat. But when there's 4 different groups, when there's 4 domains, what geometry is that? That is a tetrahedral. And when it is a tetrahedral and there's 4 unique groups, the mirror image of one to the other is not physically the same, right? It's kind of like if you took a picture of your hand, right? So here's your hand. And then your other hand, would you say that your left and right hand are mirror images of each other? Like if there was a plane and just a mirror. They're mirror images of each other, but they don't function the same way. Can your hand bend backwards and grab things in the back of your hand? Not with most people, right? Okay. So this is like this concept where you have a mirror image, but functionally they are different, is called chirality. And molecular chirality can serve, you could have a molecule that serves as like a wonder drug, or it could kill you. And if you don't engineer the right molecule in your medicine, it could have severe repercussions. Okay, so this concept, they look the same, but you really have to know, you have to understand the 3D nature of this. And so in organic chem in college, a lot what they'll do is they'll just have you guys use manipulatives and literally build these over and over and over again so that you have an innate sense, you know, yes, it looks the same on paper, but I know that these are standing on as a tripod and that one top one is coming out the top. I know where it is. And so if I understand, if I can visualize it in 3D space, when I see it again, I'll be able to recognize it better. Okay, so it's very interesting. It can make things kind of difficult because what I've shown you here is pretty simple molecule, right? That's pretty small. This can happen on a larger scale. And what happens on a larger scale, you have to take this into consideration for each one of these carbons that is positioned in whatever molecule it is, right? When there's 4 different groups, everybody hits the brakes, they stop. All right, let's figure out the chirality before we move forward, because they have to get it right. Okay, this actually happened in the 50s. There was a drug that was developed for pregnant women to reduce nausea, right, in the first term pregnancy, and they didn't realize until after, like years after, that they call it the left or the right version, okay, of the molecule, just like your handedness, left and right. The one of them was the drug, but what was also being made incidentally as a side product was the right hand version, and that was the one that was causing birth defects, right? So they got to figure it out. They figured it out now, but like before that point, they didn't really think chirality mattered. Okay. All right. So what do you need to know about chirality? Really, all you need to know is that if you see a carbon with 4 different groups on all sides, then you know it's a chiral carbon. And they're going to ask, is there a chiral carbon here? Okay, so I'm not asking you to evaluate anything beyond that. But I want you to become familiar with the term, right? Because it might pop up, who knows, in like a freshman year organic class. All right, last topic is the simple organic reactions. So let's just go one by one. There's 4 simple types. Obviously, in reality, there's way more than this. Okay, but we're just getting our toes wet here. So the first type of organic reaction is what's called an addition reaction. What does the word addition mean? It means to add something. So what they're referring to is adding hydrogens or halogens to an unsaturated compound, because an unsaturated compound has a pi bond. Like, you remember how in a double bond and a triple bond, those additional bonds are called pi bonds? So what happens is the pi bond breaks, and that break allows positions, more domains for another atom to bond to. So when we're looking here, right here, that double bond is consisting of a sigma and a pi bond. Well, the pi bond can be broken, and so let me kind of redraw it here. Right, so this guy, this is ethene. This bond here, the second one there, is the pi. The top one is the sigma. So what can happen is as that pi bond is broken, bromine atoms can swoop in So bromine atoms can swoop in here, and then they can actually, the bond between them can break. So these guys, imagine that they're bonded, but as they approach ethene, the bond between the bromine molecule breaks, and a new bond is formed between individually the carbons and the bromine. So the result is this. This is called an addition reaction because we are adding more atoms to the existing molecule. But this can only happen when there is a pi bond present, because the pi bonds are the spots where the new atoms are going to join, where they're going to bond. Okay. Now, I showed this happening with bromine, but commercially, one of the most common methods of this, or uses of this, is what's called hydrogenation. So, same thing, carbon double bond to carbon, but we're adding hydrogen this time. So the first process, because I use bromine, this is called bromination. Here, this is hydrogenation, and so on. Hydrogenation is carried out. So whenever you see a baked good in a vending machine in a cellophane packet, right, Little Debbie, right, those, why do you think those things last forever? Why will a Twinkie outlive you? It probably will. It's because of hydrogenation. What they do is they take these oils, and these oils have double bonds, and by pumping in and reacting and getting these to become saturated, it turns out saturated alkanes are more likely to be stable, right, than alkenes. And so they also have more surface area, so they solidify. So you can have an oil turn into a solid and still taste like the properties of an oil when you eat it, but it's not a liquid anymore. You heard the term saturated fats and unsaturated fats. Saturated fats are fats naturally derived from animals. Unsaturated fats are plant oils, plant fats like avocados, vegetable oil, corn oil, right? So they take these oils, they hydrogenate them, that improves the stability, right? But they don't want to use animal material in like the Twinkie. So they'll use a natural plant extract oil, hydrogenate it, and that will be the base for the oil in the food and allow it to stay, moist and edible, after like the next millennia. Okay. So you can do the same thing with chlorine, right? I mean, you can do this with any of the halogens, really. Chlorine, fluorine, bromine, iodine, hydrogen, right? Okay. So, is that clear what an addition reaction is? All right, so the next type is what we call a substitution. Well, what does substitute mean? It means one goes in, one comes out, right? So a bonded atom is displaced by another atom. So if I have some kind of alkane and I react it with chlorine, but let's say that we get one of them to come in. So Cl, for example, and methane, we could actually get formation of HCl and what we call chloromethane. This is substitution. There's no pi bonds involved. These are all regular alkanes. All right, one atom went in, one atom went out, and yeah, so fundamentally the difference between these two is that one of them involves the pi bonds, one of them does not. Okay. All right, our third type is combustion. Combustion is the oxidation of hydrocarbons in the presence of oxygen. What does oxidation mean? It means to increase the oxidation state. Where did that term come from originally? It's because elements or compounds reacted and incorporated oxygen. So when there's an uptake of oxygen to a carbon chain, that is combustion. So the products of combustion are always CO2 and H2O. All right, we learned this back in Unit 3. So How do you predict if something is a combustion reaction? Well, look, is it a hydrocarbon? Is it reacting with O2? It's combustion. Case closed. You just have to balance it. Okay, so that's actually not new. Esterification, we talked about the other day. Esterification is when you have a carboxylic acid and an alcohol react. Then you form an ester. Water is also released. Water is your second product. So, when you see an organic acid like this one, this is the acid, you can tell it's the acid because it has the acidic hydrogen at the end of the carboxylic group right here. Okay, and then it reacts with the alcohol. The alcohol has the OH. These two combine, give you water. And then the juncture between here and here. I didn't draw that right here. So let me give you an example of an esterification. I want you to finish it. I want you to draw what the product is, and I want you to name it. All right, this is what your structure should look like. Remember, it's on the alcohol, the OH comes off. On the acid, acids donate H's, so the H comes off. All right, so this junction right here, this right here is still from the acid part. Okay, so when we name this, we name it with the alcohol component first. What is the root of the alcohol here? What name do we assign to that 3 carbons? What's the root, the prefix for 3? Prop. So this is propyl. And now the second part, the part from the acid, the root is 5. So this is pent. Esters end as pentan O8. Right, so this was the root, and this is the suffix. Propylpentanoate. We get that? Okay. Our lab on Monday, you guys are going to be making 5 different esters, right? So you're going to synthesize them, you're going to smell them, you're going to draw them, classify or name them, and but you're not going to eat them because they're not pure enough to be put in foods. So you can just smell them. Okay.